Hello, everyone, and welcome to this online event covering QuEra's fault-tolerant quantum computing roadmap. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra, and it's really a pleasure to see so many of you interested in neutral atoms, in QuEra, and in fault tolerance. We've had a very exciting week last week. We announced a renewed, deepened strategic relationship with AWS, the world's largest vendor-neutral quantum cloud provider, to deliver Libra, our first fault-tolerant quantum computer, to the Amazon Braket cloud. Since then, we've been flooded with questions. How does it work? How many qubits does it have? When will it be available? How do I get in touch? Are you hiring? What comes after Libra? In this webinar, we're going to try our best to answer as many of these questions as possible. By the way, feel free to submit your questions on the Q&A box, and we'll try to address many of them after the presentation or get back to you by email with those that we wouldn't have enough time to discuss today. We assembled a team from all corners of the company. We're going to cover QuEra today, where we are and where we've been. We're going to meet Libra, understand the science behind it and the capabilities. We're going to talk about what comes next after Libra, and then we'll talk about how you can work with us and together with us. So I'd like to start by turning the stage over to Andy Ory, our CEO, to discuss QuEra today.
Thank you, Yuval, and thank you all for joining us. Let me start with who we are. QuEra was founded out of pioneering labs at Harvard and MIT, and we still collaborate with those groups to this day. We built the company on neutral atoms, which we believe is the most promising modality for reaching large-scale fault-tolerant quantum computing. Two things set us apart: world-class scientific leadership and the fact that we're the ones actually commercializing neutral atoms, turning that research into real machines. We're also expanding geographically. We've established QuEra Japan, QuEra UK, QuEra New Mexico, and QuEra Switzerland, putting us closer to the key government programs, partners, and talent in those regions. This kind of local presence, it's increasingly important as quantum becomes a matter of national strategy around the world. The rate-limiting step to building a global quantum powerhouse is not capital, but people. There just aren't enough trained scientists in the world to meet the demand of this exploding industry. But we have an unfair advantage. We recruit straight out of Harvard and MIT, and we've remained focused on science first. This has attracted fantastic scientists from all over the world to seek out employment at QuEra. We're about 200 people now, and almost half are accomplished PhDs. I'm thrilled with the quality of the folks we've been able to attract, retain, and grow at QuEra. Beyond capital, we have strategic customers. These are long-term partners we work with across system sales, cloud access agreements, and broader quantum ecosystem development. They are not transactions, they're select long-term strategic partnerships, creating real value in both directions, enabling us to accelerate our pace of investment. Government engagement and validation matter enormously in this field. Governments realize that a strong quantum program contributes to both economic prosperity and national security. Here in the United States, we're proud to be involved in DARPA's quantum benchmarking initiative, as well as supporting federal quantum efforts across the Department of Energy's national labs. Globally, we play key roles in national efforts in both the UK and Japan. Real partnerships matter immensely. What we're trying to do has never been done before, building a new type of incredibly complex machine for a global market. We will not do this alone. Scale, scope, speed, and importance dictate that we must cultivate strategic partnerships with non-overlapping core competencies. This will significantly increase our chance of success. Lastly, a properly capitalized business is a must. We've raised over $250 million with a highly technical, sophisticated investor and partner base. And importantly, that capital is focused squarely on making the first fault-tolerant quantum machines available globally. We've been well capitalized to execute on both the science and the go-to-market with a team of around 200 people, and our hiring is concentrated exactly where it matters most.
Thank you, Andy. One reason that customers believe us that we'll be delivering on our commitments is our history of delivering products both on the cloud and on premises. So I'd like to invite Alexei Belinsky to tell you a little bit about our existing products.
To tell you the story of QuEra's technology and product roadmap, we must start at its very beginnings with Aquila, QuEra's first device, first product, and the world's first publicly available neutral atom quantum computer. We first launched Aquila on Amazon Braket in November 2022, 3.5 years ago, and with 130 hours a week of availability and consistent 99% uptime, it has become the gold standard in the industry for an easily accessible and reliable quantum computing service. This has enabled customers from all over the world, across academia and industry, to publish over 60 papers centered on data from Aquila, proving a major impact of Aquila on the ecosystem. With the quantum computing stack spanning hardware and software from individually controlled atoms all the way to applications, Aquila represents an interface that is as close to hardware and atoms as possible. Our first iteration in building a series of abstractions enabling users to program a quantum device. In Aquila, users arrange atoms spatially in order to encode the problem and define a sequence of global and local pulses in order to specify the algorithm executing an analog operation mode. This programming model has enabled a number of applications in optimization, machine learning, and quantum simulations, with 2 examples from high energy and condensed matter physics shown here, 2 field opening papers from Aquila published in Nature journals by QuEra and collaborators. So these are some of the highlights from QuEra's first iteration of offering quantum computing products and services and bringing value to early customers. The next step in building towards more general utility is going to the digital mode, a gate-based quantum computing model, which lends itself to error correction and scale. QuEra's first platform offering the gate-based architecture is Gemini, which is also QuEra's first product offering for on-prem installation. The first on-prem deployment of Gemini is in Japan at ICE. Gemini offers a zoned architecture where qubits can be rearranged spatially in the middle of the computation, enabling any-to-any qubit connectivity in the processor, which supports efficient quantum circuit execution and novel error correction approaches. This leads to a special mode of operation that we are excited to announce today and launch later this year, Gemini as a quantum error correction testbed, a platform for researchers and developers seeking to build on top of the neutral atom architecture towards fault tolerance by exploring and benchmarking decoders, syndrome extraction techniques, resource factories for universal quantum computation, logical noise models, and logical circuit optimization, among many other topics at the frontier of fault-tolerant quantum computing. We are very excited to work with customers who want to build the fault-tolerant quantum computing stack with us and leverage the unique capabilities offered by the platform and by the neutral atom quantum computing technology. Of course, Gemini is just where we're getting started with this. In the remainder of the webinar, my colleagues will share where we will be going with this, with the next generation of QuEra's machines, pushing the envelope of scale, fault tolerance, and in the next few years, commercial utility.
QuEra was founded by physicists, and physicists love hardware. But even the best hardware is not useful without software tools that support the development, the simulation, the compilation, and execution of quantum jobs. Xingtao Wang will now discuss some of these software tools.
As Alexei just presented, our Gemini class machines are QuEra's first logical qubit testbeds. With that, the system also requires a new generation of toolchains and a broader software ecosystem. Bloqade is QuEra's one-stop shop for prototyping, simulating, and deploying quantum programs on QuEra's quantum computers. It runs across analog, digital, and logical systems. Underneath Bloqade is QuEra's compiler infrastructure called Kirin. Kirin is built in Rust for performance but has a Python front end as a user-friendly interface. It enables a composable, multi-level programming paradigm across circuits, QEC, atom shuttling, and pulse-level programming as well. Bloqade also supports hybrid quantum classical workflows and include built-in smart visualizations for prototyping and debugging purposes. Within the Bloqade ecosystem, we're building digital twins of current and future neutral atom fault-tolerant quantum computers. This provides the tools needed for logical scale programs. This include fast and accurate QEC simulations, realistic hardware noise models, and resource estimation tools for running logical programs. In recent months, we released 2 QEC-focused simulators to developers and users in the community. First, T-Sim is built for Gemini-class systems. It supports non-Clifford gates beyond Steam, while we provide a Steam-like API so that QC researchers who are already familiar with Steam can port their programs directly into T-Sim. PPVM, on the other hand, is our next-generation simulator and virtual machine. It supports atom loss simulation, which is an important noise characteristic for neutral atom platforms. PPVM also have native support for classical control flow, as well as stepwise execution and debugging capabilities. By releasing these advanced simulators to the public, we are empowering the community to quickly prototype QC workflows before they actually deploy these programs on real quantum hardware. Beyond the software tools, we also have a world-class team of application and solution scientists who engage in deep co-design and co-development work with our customers and partners. These highly technical partnerships are aimed at building lasting capabilities for our partners so that they can develop strong internal expertise and then be ready for fault-tolerant quantum computing. As one example, we've been working very closely with NERSC researchers in the last few years, bringing them up to speed on both analog and digital neutral atom systems. Together, we produced 7 joint publications in the last 2 years, where 3 of them are actually deployed on our Aquila system. We also jointly run a QCAN program where researchers around the world can submit compatibility proposals to access QuEra's Aquila and Gemini systems. With Los Alamos National Lab, we developed a new transversal star architecture that provides a shortcut to mega-QL scale quantum simulation. This architecture provides more than 100 times speedup compared to fully fault-tolerant architectures for specialized tasks like trotterized Hamiltonian simulations. If you're interested in engaging with QuEra on this kind of co-design project, please reach out to us. We'll be excited to work with you to translate these capabilities into real scientific and commercial value.
We believe that to fulfill the promise of quantum, it takes a village. That's why a couple of years ago, we started the QuEra Quantum Alliance, a group of leading, like-minded companies that, like us, believe in the potential of neutral atoms and want to partner with us to bring that value to customers, whether it's application development, consulting, hosting, integration, many other things. You can see many of the current companies on this slide. And by the way, applications are still open. Go to QuEra.com/partners and see if you're interested in joining the QuEra Quantum Alliance. At QuEra, we believe that the future is hybrid. This means that quantum computers will not work in isolation, but rather work alongside classical supercomputers. That's why we've partnered with some of the leading vendors in this space. We've discussed and will discuss again our partnership with AWS. We've partnered with NVIDIA to bring their GPU expertise and high-performance computing expertise together with our neutral atom leadership. At last year's supercomputing show, we've demonstrated integration with Dell QIO, Quantum Intelligent Orchestrator, that allows customers to submit jobs. QIO then routes them to the appropriate computer and then provides the results back to the user. And at last week's HPE Discover, HPE showcased some of the work we've done together, in this case, benchmarking magic states, but also in presenting the vision for integrated classical quantum computing. Neutral atoms are sometimes called cold atoms. We don't require cryogenic cooling, but because of the laser tweezers that we use, the atoms, the qubits, find themselves in microkelvin temperature. That's why it was particularly rewarding to be named one of the coolest vendors in quantum computing by leading analyst firm Gartner. Specifically, Gartner highlighted the power requirements of QuEra's computers. And I quote, "It requires much less power and much less space than superconducting or photonic computers." Thank you very much to the analysts of Gartner's for providing us with this honor. One of the areas that we pay particular attention to is the public sector. Countries, states, regions, local governments all understand that quantum computing is a strategic technology. For many, quantum computing contributes to national security, and for everyone, quantum computing contributes to economic security. Our spectrum of offering is very wide. We provide hybrid and cloud access. We can provide on-premises deployments. We work to do application code development. And in particular, we work to do workforce development and start up research and development programs so that the local talent can use these computers to their fullest extent. On the left, you see examples of many of the places we've worked at and are working with. DARPA, we're part of QBI, Quantum Benchmarking Initiative, the UK, National Computing Program, AIST in Japan, and as well as regional partners like Roadrunner Venture Studios in New Mexico and MGH-PCC here in Massachusetts. But enough about today. Let's talk about tomorrow. For this section, I'd like to start with Professor Vladan Vuletic, MIT professor, co-founder of QuEra, and our CTO today. Please, Vlad.
Thank you, Yuval. Here's the key point I want you to take away from this section, that our roadmap is built on peer-reviewed, top-tier published research from QuEra and our university collaborators. The system spans 3 layers: the hardware primitives at the bottom, the quantum error correction architecture in the middle, and the system-level mechanisms that tie it all together at the top. In particular, you will hear in the following parts about a new generation of machines that operate continuously and where atoms lost during the computation are being replenished. Over the next several slides, I'll show you the published papers behind each technology component. Let's start with a landmark result that was published in Nature. This was the world's first logical quantum processor based on reconfigurable atom arrays. This work demonstrated logical algorithm execution using a zoned architecture, which had a storage zone, a quantum computation zone, and a readout zone for error correction. And with this zone architecture, massive parallelism, and non-local connectivity by moving atoms, we implemented 48 logical qubits with over 250 physical qubits. This work also demonstrated below-threshold error correction and parallel logical operations. This is the result that demonstrated that neutral atoms indeed offer a realistic path to fault-tolerant quantum computing. In another work, published also in Nature, we put it all together. This is an experimental demonstration of all the required elements for a fault-tolerant neutral atom quantum computer end-to-end. We worked, or we achieved below a threshold error correction by a factor of over 2. Up to 96 logical qubits were demonstrated in the system, and 100 times increase in cycle rate that resulted from using non-destructive spin-resolved qubit readout. We put all together all the pieces by now into one system. This is the experimental demonstration showing that the architecture holds up as a whole. Now, quantum error correction is not only about the quantum error, it is also about figuring out, based on the measurements results, which quantum error actually occurred, which requires considerable classical computing cost. This is the process of so-called quantum error correction decoding. And this classical overhead can easily become the bottleneck. Here we used so-called correlated decoding or demonstrated correlated decoding for the first time, published in Physical Review Letters, where we decoded across multiple logical qubits jointly. This provides advantages. It gave roughly a factor 1.5 improvement in logical error, and what is even more important, it cuts the number of syndrome extraction rounds, the number of error detection route, by a factor of the code distance. This implies faster computation as less time is spent on detecting and correcting errors and more time on the actual computation. Another feature that is very important is the efficiency. One huge advantage that neutral atoms have compared to other platforms is a very good non-local connectivity, meaning that we can connect qubits with quantum gates that aren't originally physically next to each other. This is achieved by moving the qubits with the help of laser beams to new locations. This, for instance, will allow us to use high efficiency so-called QLDPC, quantum low density parity check codes, with constant overhead. This particular result, published in Nature Physics, showed that it is possible to reduce the number of required physical qubits by more than a factor of 10 compared to the surface code at 3000 physical qubits scale. Requiring fewer physical qubits to realize a certain number of logical qubits will be key to reaching the utility scale quickly. Here is another important piece published in Nature. This was showing low overhead transversal fault tolerance. Here we can reduce the total number of physical operations and get down to a single syndrome attraction round per logical operation, which allows us to have a factor 10 to 100 improvement in time to solution for logical applications. This is significant in turning a possibly week-long computation into a day-long or hour-long computation, this improvement.
Thank you, Vladen. I'd like to switch now from the scientific foundation to what actually is being done in QuEra as far as the engineering and work to build these machines. And for this section, I'd like to invite Alex Lukin and Sergio Cantu.
To turn the scientific advancements into fully functional quantum computer, we need to develop multiple core functionalities of our machine. One of the key components is enabling the quantum error correction, which requires our two-qubit gate fidelities, the fundamental building blocks of quantum computer, to be below certain threshold. And in the neutral atom community, we have been doing a steady job of improving on the two-qubit fidelities. And in particular, in the past few years, the state-of-the-art system has surpassed this threshold, and among them were QuEra machines that have been showing a steady progress for the past 2 years. Our latest system have demonstrated 99.77% two-qubit gate fidelity, which improves to 99.96 if we post-select for loss. And this is an important metric that will allow us to improve on the effective thresholds required in our system. In addition, we have been working on extending these results to large zones, where we have now demonstrated an average fidelity of 99.74 over the large region. Another critical feature that is necessary to enabling MegaQOP and beyond quantum machines is ability to operate these processors indefinitely, which means that we need to replenish some atoms that inevitably get lost during the computation. Along these lines, our collaborators at Harvard have de-risked the architecture that can deliver the atom flux from a separate chamber. At the same time, here at QuEra, we have completed the prototype design and already commissioned it into operation, where we have a machine that separates the initial atom loading into the separate chamber compared to our computational zone. That allows us to bring about 20,000 atoms per second, which should be compatible to operating a machine consisting of 20,000 physical qubits. We also have been making a steady progress on developing structural components of logical algorithms. In particular, one of the most important parts of the quantum algorithms is generation of non-Clifford gates. And I'll pass it to Sergio to tell you how we're planning to do this.
Thank you, Alex. From this state-of-the-art components, we can orchestrate sub-processes to enable Libra's universal fault tolerance. A key sub-process is non-Clifford generation, also known as magic states. These states necessary for non-Clifford gates. These are the operations to make a quantum computer universal. We published in Nature the first logical magic state distillation, carried out entirely on logical qubits, demonstrated on a Gemini system that is now in Japan. We ran a 5-to-1 distillation at both distance 3 and distance 5 color codes above the distillation threshold of 83% for the distillation code. And in each case, the distilled output fidelity exceeded the input. We have shown that the missing ingredient for universal fault-tolerant computation works in practice. Now let's cover Libra's feature set. The first feature is that Libra is a mega-QoP class system. It's built to run about 1 million reliable logical operations in a single computation. It reaches that scale through continuous operation, reloading atoms on the fly so the machine keeps running without resetting. The second feature is that Libra packs more than 10,000 physical qubits into a single QPU core. From those, we can encode up to 256 logical qubits. The third feature is that Libra runs universal logical computations. The target logical error rate is 10 to the minus 6, and that's about 1 error per million logical operations, which is what mega-QoP scale work needs. At the same time, Libra showcases very large parallelism, which lets us handle qubit storage and ancilla management at the logical layer. It also enables us to run transversal operations at scale. And the last feature is that Libra is our first system with real-time quantum error correction. Errors get decoded and corrected as the computation runs. I am happy to announce that the Libra system is under construction today, with a collaborative effort of QuEra's talented scientists and engineers, as well as our QEC scientists.
Thank you, Sergio. Libra will be the first fault-tolerant quantum computer coming to the public cloud. The foundational capability of the Libra system is 256 logical qubits at 10 to the minus 6 logical error rate, enough to run 1 million operations. Logical qubit performance is our central focus as we enter the era of fault-tolerant quantum computations. The Libra architecture lets us take advantage of high encoding rate quantum error correction codes enabled by O2O connectivity. As a result, we expect to reach this level of logical performance with just over 10,000 physical qubits. We implement these codes efficiently through parallel transversal logical operations, reducing the time to solution. Our neutral atom system gives us a reconfigurable multi-zone architecture. Libra has separate zones for memory, computation, and a magic state factory, and we can reconfigure the qubit resources to optimize for each application. It will also feature continuous qubit loading through a dedicated reservoir zone, replacing atoms lost during long computations to sustain performance. Libra operates at room temperature with no need for special cooling systems like cryogenics. It consumes less than 40 kilowatts, less than a single AI server rack, and fits in under 1,000 square feet. These modest requirements make Libra straightforward to deploy right into existing data centers. In 2028, we will launch Libra on Amazon Braket as part of an expanded partnership with AWS. Eric Kessler, general manager of Amazon Braket, put it this way: QuEra's technology has demonstrated a clear path to fault-tolerant quantum computing for Amazon's customers. we are honored to have Eric's endorsement. Our strategic partnership with Amazon is built on 3 pillars. First, proven science. As Vladan, Alex, and Sergio described, QuEra, together with Harvard and MIT, has proven the science of scalable, fault-tolerant quantum computing. From high two-qubit gate fidelity to continuous qubit loading to magic state distillation to an end-to-end demonstration of logical qubits. Second, proven in production. As Alexei explained, we've worked with Amazon for more than 3 years, and we've proven we can build, deliver, and operate quantum computers at over 99% uptime. It wasn't easy, but we persevered and served our customers with real professionalism. Third, commercial momentum. We believe the next generations of QuEra's quantum computers, starting with Libra, will deliver significant utility, and AWS will be a critical partner in bringing our quantum computers to customers. We could not be more excited to expand our partnership with AWS. Our technology and product roadmap is accelerated by AI and by our collaboration with NVIDIA. As QuEra's strategic investor and technology partner, NVIDIA helps us fully leverage AI to boost the performance of quantum computing. Let me give 2 concrete examples of where AI accelerates quantum computing: QEC decoding and calibration. QEC decoding is a task of translating the error signals collected from the system into the right correction instructions. As Shintao explained, this requires substantial classical computation. The impact of AI here is direct. Faster, better decoding leads to faster, better logical qubit performance. And we will build AI right into our QEC architecture. We've already seen strong early results from our QEC decoding work with NVIDIA, and we will build on them. Calibration is critical to improving and sustaining the performance of logical qubits. It means collecting system data, telemetry, syndrome extractions, identifying where the system drifts from its ideal state, and applying the right corrections. This is a problem with a verifiable outcome and clear context, exactly where AI has proven most effective. Automating it not only improves stability, but lets us reach better performance through faster, more accurate feedback. And these are only the tip of the iceberg. Without a doubt, AI will dramatically accelerate the progress of quantum computing, and our architecture will place AI at its center. We are excited to take this journey with one of the best partners we could ask for, NVIDIA.
Libra is an exciting step, but I know that many of you are interested in understanding what's next. So I'd like to turn it over to Milan Kronjaka to talk about some of that.
So before asking how do we scale beyond Libra, it is useful to look at an example of how do we think about efficient QEC architecture design for Libra itself. And there, quantum simulation is one of the workloads that really fits Libra naturally at the mega QOP scale. And an example of how do we think about concrete implementation is QuEra recent BB star architecture, where we concretely co-design QNC architecture to the quantum simulation tasks. The key point is that we are not choosing the algorithm, the code, and the hardware implementation independently. We start from the structure of the target application, which in this case is local lattice Hamiltonian simulation, and use its fundamental ingredient, which are lattice translations and problem connectivity, to guide the compilation, the code design, and the implementation. And these symmetries lead us naturally to high-rate bivariate bicycle style quantum codes, where the required structured Clifford operations and small angle magic can be performed in parallel across all logical qubits in the block. And on neutral atom hardware, the same translation structure maps onto fast, low depth, highly parallel acousto-optical deflector shifts. The result of all of this is a huge reduction in space-time cost for Libra-supported prototypical megacube simulation applications. Mainly, here we're showing that quantum dynamics of transfer field Ising model and Fermi-Hubbard model, compared to what the same workload looked only a few years ago, can be brought down by orders of magnitude, with roughly 100 times fewer physical qubits required and 1,000 times less runtime. And crucially, these kinds of improvements are enabled by flexible hardware connectivity, which make rapid architectural exploration and iteration viable in the first place. So here's the key takeaway. Careful QEC architecture co-design around the application and hardware strength can really move the roadmap, not just complement hardware scaling. And the natural next question is, if this is what the co-design can do at the megacube scale, how do we use the same philosophy to scale beyond Libra toward gigacube architectures? Reaching gigacube efficiently means we have to overcome several major sources of overheads introduced by quantum error correction. So let me first introduce these and then talk you through on how do we think about dealing with these at QuEra. So the first big source of overhead is the space. How can we efficiently encode logical qubits using physical qubits? The second overhead is time, which is really closely tied to how many logical gates do we need to do and how do we efficiently executing in a fault-tolerant fashion. And even with more efficient quantum codes that we have today, runtime is still a major challenge. For example, several recent approaches reduce the physical qubit requirements for the Shor's algorithm to around 100,000 qubit range, but the runtimes that we get are still on the order of years. And then finally, quantum error correction also poses a substantial demand on the classical side, where error decoding is itself a complex combinatorial optimization problem. So let's look at how QuEra's future gigacube architectures are designed to exactly address these overheads. So let's start with space. How to reduce the number of physical qubits we need to encode each logical qubit. And as I already mentioned, until recently, much of the error correction relied on the surface code. The main reason is that it is well matched to short-range fixed connectivity, which is easy to implement in most hardware modalities. And it supports straightforward access to individual logical qubits during computation. But as we know, encoding rate is really poor. It often requires hundreds, even to 1,000 physical qubits per 1 gigacube capable logical qubit. But luckily, recent QEC code advances can improve these drastically. And the key enabler there is moving beyond strictly local connectivity. If you have long-range connectivity, even fixed one, you could design codes such as bivariate bicycle codes that can reach encoding rates of about 10 to 1, while still supporting families where you can directly address most of the logical qubits. At the more aggressive end, QuEra's recent work has found ultra-high rate code families with encoding rates as low as 2 to 1, and with logical memory error rates down to even 10 to the minus 13 regime. This would effectively solve the memory problem and the space overheads by utilizing the flexible long-range connectivity to the fullest extent. The trade-off is that addressing individual qubits becomes more complex. So really, the idea here is by using more long-range and more flexible connectivity, we can drastically reduce space, but we are unlikely to use one code everywhere. Different architectural laws like memory, operations, and magic may benefit from different codes, or we can, along the way, discover better codes for each. So we really also need ability to reconfigure architecture around these new codes. And this is where QuEra's flexible connectivity, parallelism, and heterogeneous zones become essential. They really let us combine the best codes for each role within a single device architecture. How about time? Once we choose good compact quantum codes, the question that you already posed is, can we operate on them fast enough? We need syndrome extraction, logical gates, and magic state generation to be both low depth and high throughput. And here we show two examples of how do we think about efficient operations at QuEra. The principle behind both of them is co-design around hardware strengths. And the first example tackles the most common operation in fault-tolerant quantum computation, which is the code syndrome measurement that allows us to be fault-tolerant in the first place. And in QuEra's recent work for ultra-high-rate codes, we already looked at, we did not only find well-performing 2-to-1 encoding rate codes, we specifically search for code instances where we have some hidden structure, hidden symmetry that can be used to perform control-efficient syndrome measurements, and specifically with the controls that use our highly parallel acousto-optical deflectors. And the second example tackles one of the most expensive operations on the other side, which is typically magic state generation. And recent Harvard work there showed that magic can be generated directly in high-rate codes, specifically the so-called tricycle codes, where in low circuit depth and using only highly parallel transversal operations, we can generate a CCZ magic gate. Since magic state generation is often the dominant time cost in fault-tolerant algorithms, reducing this overhead directly improves time runtime. So again, with flexible connectivity, parallelism, and reconfigurability, we can make high-rate codes practical, not just compact. So the last major overhead to tackle is on the classical side, the decoding. Even if we make quantum compact, and even if we optimize the logical operations, quantum error correction still requires us to process syndrome data and decide which corrections to propagate. This is a hard combinatorial problem, and at giga-cube scale, we simply cannot allow classical decoding latency to bottleneck our quantum computation. And the idea to solve here is simple: move the hard work, classical hard work, away from quantum runtime. In the recent Harvard work we show here, a convolutional neural network decoder is trained offline to learn high-quality decoding strategies for classes of QLDPC codes. And then during quantum execution, we only need to run inference. This gives us two advantages. On one hand, we get better decoding performance due to the expressibility of our neural nets, around 17 times improvement in logical arrays compared to existing bicycle code decoders. But more importantly, we can dramatically lower latency with improvements in the 1,000 to even 100,000 range in terms of speed up. So the theme here is the same. We use careful design to move classical complexity where it belongs and keep real-time quantum execution as fast as possible. So what does this all lead to? If we can reduce the space, the time, and the decoding overheads of the quantum error correction at the architecture level, how much can that compress the roadmap to useful giga-cube scale quantum computation?
As a special treat, and to give you an even broader peek into the future, I'd like to pass the stage now to Professor Misha Lukin. Misha needs no introduction, but nevertheless, he's a professor of physics at Harvard. He's co-founder of QuEra. He's the chief science officer of the company. And I think that, like Vladan, we wouldn't be here without Misha's ingenuity, persistence, and work. Misha, the stage is yours.
Thanks, Yuval. I would like to step back a little bit and emphasize that in the past few years, there has been dramatic progress in both hardware capabilities and also in reducing the cost of fault-tolerant algorithms, thanks in part to the techniques that Milan has talked about. I want to emphasize that neutral atom systems are uniquely suited to take advantages of these novel developments, in particular in both high-rate and ultra-high-rate codes, because they feature programmable connectivity, efficient control, and thanks to the recent advances at QuEra, Harvard, and MIT, the ability to operate the systems continuously, enabling the access to deep circuit quantum computation. In light of this exciting development and accelerating progress, I would like to provide a peek behind the curtains about our future plans. On the top of what we already discussed in this webinar, namely Libra mega-QoP system being available on AWS starting in 2028 through the combination of both hardware and software upgrade, we are going to realize a system of over 1,000 logical qubits capable of executing over the billion quantum operations. Arriving quite a bit earlier than what many people expected in this field, this will mark a very special moment in time, something that we as a community have been working on for the past 4 decades. While we don't know at this point what the systems with unprecedented quantum computing capacity will be able to accomplish, we are certain that they will allow us to enter and explore the corners of universe that no one has been able to do previously. We realize that making this vision a reality is extremely ambitious and challenging goal, and we invite you to join us on this exciting journey.
Thank you very much, Misha. As we head towards the end of our webinar today, I'd like to talk about how you can join us and how you can work with us. As Misha said, we live in a special time. Quantum computing is about to change the world. And this is your opportunity to join the company that's building and leading the F2QC era, the fault-tolerant quantum computing era. As of this morning, there were over 70 open roles on QuEra.com/career. They span a wide range of disciplines, from physics to quantum error correction, engineering, computer science, commercial, administration, finance, you name it, it's there. It's hard to imagine you could not find a position that's attractive to you at QuEra. And why work at QuEra? It's a company that's leading in the science and not leading in science fiction. We try to be honest and transparent with our work. We are committed to the highest quality, no shortcuts. And this is a chance for you to work and learn and enjoy the company of some of the industry's best and brightest. So I invite you to explore our careers page and see if QuEra is right for you. Libra and the systems beyond it open new opportunities. They really take us into uncharted corners of the universe. And we want to partner with like-minded enterprises, service providers, governments, academic institutions to really find how quantum could be immensely useful, to determine where quantum could work for you. We're looking to find the best applications. We're looking to partner with people who want to invest the time to co-design a solution. We're looking for people that can help with strategic influence on our roadmap and capabilities. And of course, if we find together an application that's attractive, that can fit into capabilities of our system, we will provide computing time so the application doesn't remain on the drawing board, but actually is calculated. Go to QuEra.com to get started, and we can't wait to see what you have in mind. Hello again, everyone. Thank you for sticking with us for this presentation. I'm joined here in this room. I'm Yuval, Chief Commercial Officer, Andy Ori, our CEO, Takuya Kitagawa, our President, and Ed Durkin in the back, our CFO, and remotely, Professor Vladan Vuletic, who was not in this room right now. So first, thank you for all the interest and all the fascinating questions that were sent. We're going to try to address as many of them as we can, but the rest we'll try to respond by email. First question, maybe Andy, you want to take it. How are you planning on maintaining and accelerating a commercial momentum until Libra's launch in 2028?
Wow. Well, there's a lot of work to do to be prepared for Libra. Libra is coming, and will we as a world be ready for Libra? So there's a lot of co-design, a lot of algorithm work. There's a lot of exploration with our partnerships. So we're actively engaged, and we look forward to people coming to us with some serious ideas, and let's collaborate to find ways to be ready in 2028.
Vlad, I have a question that comes often, and maybe you are best equipped to answer it. The jump from a few hundred qubits to 10,000 qubits, the jump from the megaquark to the gigaquark machine, isn't that too fast? How is that feasible?
It's a very good question, and people are right to be skeptical. At the same time, we have published research from, for instance, the university labs showing already, more than 3,000 qubits being prepared and being continuously replenished, which is a key technology. So something that has emerged newly over these years and enables these megaquark and gigaquark machines is the continuous reloading and replenishment of atoms, which has been demonstrated and reviewed and shown in peer-reviewed journals. The exciting other thing that is happening is that from the algorithm sides over the last year or two, about last 2 years, very exciting developments have happened that show that with novel codes, one can encode logical qubits much more efficiently into physical qubits. And what we have been, among other things, working on is to update and improve our shuttling and atom movement capabilities so that we can also implement in hardware the logical codes. So it's basically a combination of hardware improvement over the last years and also great improvements on the software and algorithm side that enable the execution over the roadmap as we presented now.
Thank you. And Takuya, maybe you could answer, what use cases can customer target for the Libra system?
Libra system. There are, I think, many examples of application that we are extremely excited about. But as maybe one example I want to highlight is really, what Milan talked about, which is, this new architecture of, BB and star that's published probably today, actually. That, architecture, uniquely is suited for doing a quantum simulation for materials. And it will allow us to actually do a pretty substantial simulation there. So that's one example I'm really excited about. But frankly, other examples such as chemistry, optimizations, and drug discovery are all the target use cases that we are excited to address. And if anybody has idea, what ideas they want to try out, please do contact us, as Yuval explained at the end.
We discussed QEC codes, and there's a question from the audience about whether users will be able to experiment with their own QEC codes and also perhaps with their own decoders. Maybe either Vlad or Takuya, do you want to take that?
Takuya, do you want to say something?
Can you repeat that question one more time?
Whether users will be able to experiment with their own QEC codes and could they use their own decoders?
Yes. So I guess it's already in the Gemini. We will allow people to experiment with a few ideas of QEC code and also decoder. But going into Libra, that's our intention generally. We want to give our users as much flexibility as possible to experiment with the ideas. Frankly, I think at this stage of quantum computers, it's very important to co-design applications with some of those QEC ideas and decoder. So we would like to collaborate with the customers to develop this product together and generally try to provide as much flexibility as possible. Vlad, would you like to add more comments?
Maybe just an excellent answer. Just we will try to give access at different levels to the users and also the users of different expertise. So we will provide access on different levels and work with users to realize exciting ideas, including new decoders.
Ed, this is quite an ambitious roadmap. Are we sufficiently funded to perform it?
We are sufficiently funded. We announced a successful financing in 24 and 25 with Google, NVIDIA, and others participating, and we're liquid and well capitalized today.
There's a recurring question that I answered sometimes live, but I want to, it came up again now. People are asking about the software interface for Libra and additional systems. On one hand, some people want to work at the very high level. Oh, I have a Qiskit program or a QASM program. And on the other, some people want to work very, very close to the hardware, even in atom moves. We have a layered software architecture with well-defined APIs in every layer. We're going to open up several of these. We already have opened up several of these today. And I think that for close partners, we might open some of the others. So wherever you prefer to work with QuEra, we will try to find a way to accommodate you.
And it is also like learning, process for us as well to get the feedback from all of you, users, to understand what your needs are, and then we want to incorporate some of those, demands into our product.
There's a reverse question here. We answered what workloads would be relevant for Libra. Someone asked what workloads will not be relevant for Libra.
Oh, that's an interesting question. Well, I mean, people's creativity is, there's no limit to people's creativity. So I don't think anything is out of scope, in my opinion. And I would just challenge ourselves to try to figure out a way to implement many of the ideas, good ideas, people have into our machines. Yeah.
But for instance, we don't think that Shor's algorithm could run on Libra.
Well, depending on the scale, but yes, that's generally the case. Yes.
Vladan, would you like to add anything?
Yeah, we will not run RSA 2048 on Libra.
Right.
I can say as much.
We spoke about the open positions on QuEra.com/careers. Is there a particular area that we're looking to hire, Andy? Is it physicists? Is it software engineers? Is it finance and administration people? What are we primarily looking for?
Well, finance.
Yeah.
G&A, right?
No, I mean, look, we're building a business. This is a translational business where the science isn't done, it's ongoing. We need scientists. At the same time, we need to engage with the community to understand how this science could build technology and products and fit into markets. We need to be able to amplify what we make while we support the continued science. And so we need to translate that into production. We've demonstrated that we can run systems with 99+% availability on the cloud, and that we can ship systems, in this case to Japan, halfway around the world. But we need to amplify that. And we need people that help us from all of those areas. And then, of course, we are a business. And so the go-to-market side as well. Partnerships are really important to me. I don't want to have to invest money and time into things that partners could help us with while we focus on the things we're really great at. But it really is across the entire spectrum of the business.
I want to provide two
Maybe
quick
I can
answers.
jump in, just make a quick pitch. Yes, Andy is right. We're looking across the entire spectrum, but particularly close to my heart is the science engineering interface.
Yes.
If you know a great systems engineer, basically we are building here the rocket ship. We're trying to land on the moon, but with a quantum computer. And so it's a very significant science engineering integration challenge. And we are looking particularly, all areas, but particularly for great people who are interested in this challenge.
Thank you, Vlad. Absolutely.
Two quick answers before the next question to Vladan. So first, Libra is a digital gate-based system. It's a universal quantum computer. Second thing, this webinar replay will be available typically within 24 hours. There's a question that maybe you can help with, Vladan, about the bottlenecks. What are the scaling bottlenecks? Is it laser power? Is it optical control? Is it vacuum stability? Another option here is cryogenics. I think that's probably not the scaling issue, but what are the scaling challenges?
Some of the ones you mentioned are certainly, although, for instance, in terms of laser power and optics, we think we can scale to 100,000 physical qubits with known technology. We're, of course, thinking also potentially one day to scale to 1 million. One of the challenges is, our connectivity is the biggest feature of these neutral atom systems, the fact that we can move qubits physically and therefore implement codes very, very efficiently. One of the challenges is to move large groups of atoms in complicated patterns that allow us to realize these newest, very, very efficient codes. And if we meet this challenge, we will have, we will meet the algorithms halfway, and we will have, a very well operating machine opening up many new possibilities.
How are you thinking, Andy, about geographical expansion?
Yeah. I mean, it's a global opportunity. We've already crossed the Rubicon where we need to put operations closer to where the opportunity is. in Japan and England and Zurich, and throughout the United States. That it just has to be. We do have our center is here in Boston, largely because there's unparalleled access to phenomenal science. At the same time, where we have been and we will continue to be a global operation.
And maybe next to last question before Andy, maybe you have some closing comments. But a question came up about optical interconnects that typically comes up with systems that are more limited in scaling. But are we planning an optical interconnect between multiple QPUs, and if so, how soon?
So generally, we believe, all the machines we discussed, today, including Libra, MegaQuop, and GigaQuop, we can accomplish them within a single system. So that's the confidence we which have, to achieve these goals. In terms of, the future, much later, future, perspective, maybe Vladan, if you have thoughts, maybe you can add.
In the far future, of course, we know from classical computing that once you have classical computers, you want to connect them. And so you want to connect eventually quantum computers with a quantum connection. That being said, our density of qubits with neutral atoms is extremely high. And in a kind of few millimeter square chip, we can fit 100,000 qubits and connect them directly. So we have no immediate plans for the MegaQuop and GigaQuop machines to use interconnects simply because they are not demonstrated yet. At the same time, we encourage new ideas, experimentation, and so on. And I think eventually, everybody will want quantum networks to connect multiple quantum computers together, but it's not on our roadmap till 2030.
Before I turn it over to Andy, if you're in Boston this week, come see us at Quantum Tech or plenty of events. We'd love to continue this conversation offline. With partners, with collaborators, with potential employees. And Andy, any closing thoughts?
So I want to say thank you. Yuval, great job. Trevor is in the room with us. Thank you. Great job. This is the result of 7 years, 200 folks here, and countless folks at universities, partners, and government labs that have worked with us. This is ambitious. Vladan is right to say people ought to be skeptical. We have not talked about any forward technology for 2.5 years, largely because we've been very surprised at how quickly the science has evolved. Our confidence has increased. This is ambitious, but it is doable. And we want to work with all of you because this is something that belongs to everybody. And it is going to take a big community to bring quantum globally so that we can realize the benefit. It's going to happen sooner, and it's going to be really, I think, wonderful. So please engage with us, and I hope you all have a good rest of the day.
Thank you, Andy. Thank you, Ed, Trevor, who is not in the picture, and everyone else that participated in this webinar. Thank you for joining us, and please continue to visit us both physically as well as on QuEra.com.